Hello, 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 people of the world. So today we are going to talk about mechanics, classical mechanics. Okay? Classical mechanics, what is mechanics? How do we solve mechanics problems in an efficient way? And why do we struggle so much with Newton's laws? Why are they so hard to implement? Okay. So Newton's laws. How do we solve problems in Newton's laws? Well, it goes something like this. Well, we have some sort of forces, right? We have forces, and then these forces, we're going to set them equal to ma, correct? And if we have multiple forces, then we're going to do like this. Sorry, this should all be vectors. F alpha is going to be m r alpha double dot, right? Where alpha is from 1 to the number of parts of the system, right? Imagine we have a system like this. We're going to have like 1, 2, 3, 4, 5. We're going to have a certain amount of parts, and we have to find the force on each one of these parts. And a nice compact way to write this is by using alpha. So let's say F1. F1 is going to be the force on particle 1, and so on. And this is just the second derivative position. Okay, so we have F equals ma. Second step is to break up into components. Right? If we have some kind of complex system, we want to break it up. It's, for example, f alpha x is equal to m r alpha x double dot. We want to break it up to the x component. We want to break it up sometimes into the theta component, into the angular components, right? It's just very tedious and so on for all the components that we need. Sorry. And then we solve for r alpha, right? The whole point is to solve for a position. Now, this can often be an extremely difficult procedure because sometimes it's very hard to break it into components, and furthermore, it's very hard to solve this equation in terms of r alpha double dot. Right? So, and above all, it takes into account constraint forces. Right? Let me give you an example of this. Let's say we have a incline and a block on the incline. So what's stopping this block from going onto this incline? Well, there's a constraint force equal to the normal force, right? The normal force is stopping this block from completely going through this incline out the other side, right? That's why this motion has to be constricted. So in Newton's laws, we have to take into account this n, and usually you would break it up into n, whatever sine of theta, and n cosine, and such so forth. Mg cosine it's so tedious because you have to take into account all these constraint forces. Okay, no more. There's a much simpler way. Here we come to Lagrange. And what does Lagrange say? Lagrange is very smart. Long time ago, Lagrange said, "Oh no, Newton, this is all wrong. These constraint forces, they're no good. Constraint forces, we do not like constraint forces." So what did Lagrange say? Let's get rid of them. Lagrange said that we had a lot of positions, right? We had a positions, R alpha. And let's just see here. We have these R alphas, but they can use some work. What do I mean by that? Well, let me start off not with R alpha, but let me start off with a dynamical system. What is a dynamical system? Well, a dynamical system is just a system that can be uniquely represented using dynamical variables. This is a very easy definition, right? A dynamical system, let me give you an example. A particle in 3 dimensions, right? The dynamical system is the particle and a system that can be represented uniquely using dynamical variables. So we have the system, this dynamical system of the particle, and it can be represented uniquely with its position, which is x, y, z, right? These dynamical variables x, y, z they represent the dynamical system of the particle. That's what a dynamical system is. Okay, and if we have a bunch of these, as I said before, we have a bunch of these particles, then we're going to have our alpha. We're going to have all these different positions for each particle, where alpha is from 1 to the number of parts. And usually I just call this m, right? Because it's arbitrary, it doesn't matter. And let me give you, and the systems that we want to consider, right? We can have a million of these particles, all have the same equation of motion. But what we want to consider is something like this. We want to consider systems that are constrained. Very important, right? Unconstrained systems are trivial. They all have the same equation. F equals 0, F equals 0, ma equals 0, F equals 0. They're just free particles. We don't care about them. They're trivial. We want to consider systems that are not like this. We want to consider systems that are constrained. For example, a rigid body. Right? Look at this body over here. Sure, it has 2 particles, 2 masses, whatever you want to call it, but they're constrained that they must be separated by this line, this distance L. This distance L cannot be longer, it cannot be shorter. This distance L is finite, right? This is the constraint, that they must have a separation distance of L. So that's our constraint. Now, let me move on to degrees of freedom. Degrees of freedom. What's the degrees of freedom? Well, degrees of freedom is very simple. Degrees of freedom is just the number of dynamical variables we need. Very simple. Oops, sorry. Very simple. The dynamical variables. So consider the 3D particle. How many degrees of freedom will it have? Well, as we said before, you represent it using the position x, y, z. I count 3. X, y, and z. Right? Very simple. The degrees of freedom is just the number of dynamical variables. And if we have m particles, then so forth is going to be 3m degrees of freedom. Right? You just multiply by the number of particles. And if we have n constraints, whoops, sorry about that. And if we have n constraints, is just going to be 3m minus n. Right? For example, we have these we have 3m degrees of freedom for well, how should I say it? For just regular particles, for free particles, no potential, no nothing. We have 3m degrees of freedom, right? They can move in x, y, and z. But if we pose some constraints, like that their distance has to be limited, they can't turn some kind of angle, right? Then you subtract the number of constraints. So that's the amount of degrees of freedom. So let's consider this rigid body as an example. Pause this video and ask yourself how many degrees of freedom, and then come back to me. Okay, so how many degrees of freedom? We have 1 particle here, 1 particle here. So that's for the first particle 3 degrees of freedom, right? We're considering x, y, and z. For the second particle 3 degrees of freedom. And now minus the number of constraints. How many constraints are there? There's one constraint. What's the constraint? The constraint is that it is the separation has to be L. So 5 degrees of freedom. Okay, very simple. Now, let's keep going. Let me make a new page actually. So what do we have? We have dynamic systems, dynamic variables, degrees of freedom. Degrees of freedom is the number of variables we need. So we can generalize this. Generalized. So for any generic system, these dynamic variables, dynamical variables are known as generalized coordinates. And this I will be talking about a lot. Right? Why is that? Well, I'll tell you why. Consider a system, right? We have R alpha is a position. The alpha position, it could be the position of particle 1, of particle 2, is just a position, okay? And let's say the position is a function of x, y, z. Okay, that's fair enough to say. For example, a particle, 3D particle, as we said. Okay, yeah. So, why x, y, z? Why? Well, as you know, XYZ is not always the most useful coordinate system. This is Cartesian, right? But we can also write this as one and the same as writing this as a function of r and theta, polar coordinates. If you want to be exotic, you could even write this as a function of cylindrical coordinates. Z. Ooh. Or cylindrical type objects. Right? This would be Z. This would be R. And that would be theta. So this the dynamical variables have no dependence on the coordinate system, right? You can choose any dynamical variables that you want, right? The x, y, and z, they're all dynamical variables because they uniquely represent the system. Okay? So as I said again, for the last time, these dynamical variables can take on any form they want. They are what's called independent of coordinate system. Dynamic variables. And that's very important. Dynamical variables are independent of coordinate systems. Right? R theta z, x, y, z, whatever you want. And that's why we call them generalized coordinates. Because they could take on any general form. Starts to make sense now, right? They can be r theta, it could be whatever you want. That's why they're called generalized coordinates. And generalized coordinates we denote as qi, where I is goes from 1 to the degrees of freedom, right? We have q1, q2, q3 for a 3D particle is equal to x, y, z, right? The number of degrees of freedom is 3, and the number of generalized coordinates is 3. So the qi's, this makes up the qi's, they are, the number of i's is the degrees of freedom. Okay, very easy to see. Generalized coordinates, very important. So now let's keep going. From these generalized coordinates, Lagrange did something phenomenal. He completely reformulated the equations of motion. Right? The equations of motion in Newton is just F equals ma, and then you solve for r double dot and whatever. But here we have something different. I'm not going to go through the derivation. You can look it up. It's not hard. But you plug in some kind of derivation. You derive. It's not a hard derivation. You use generalized coordinates and you use r alpha. So you use r alpha, use the generalized coordinates qi. And you know that the r alphas are functions of qi's, right? R can be a function of x and y. R can be a function of r And theta, it can be a function of anything. It's a function of the generalized coordinates. And it could also be a function of time, right? Remember circular motion? We have cosine omega t. It's a function of time, right? So it can be a function of time as well. And then you do some derivation, and you get this. You get that, well, you get this equation. Oops. This is what you get. Now, what is this called? This is called the Euler, Euler, whatever you want to say, Lagrange equations. After Euler and Lagrange. So, what's L? dl, dq. Qi is just our generalized coordinates. Qi, I'm not even going to write it. Right? Qi is just our generalized coordinates, our dynamical variables. L is the Lagrangian, is defined as the kinetic energy minus the potential energy. The derivative, you know derivatives, Qi dot is just the derivative of the generalized coordinates. Right? It's just Leibniz notation. And Qi is any non-conservative forces. Because when you formulate the Lagrangian, the potential, you only put in there conservative forces like gravity, springs, and whatnot, right? But where in this equation do we put non-conservative forces? And that's in this. Capital Qi. Because think about it this way. In thermodynamics, you have Qi, right? It's the heat or something like that. And this is analogous to classical mechanics because Qi represents the non-conservative forces such as friction, which are dissipative, they give off energy. Okay, but usually Qi is 0 in the systems that we like to work with. So then our Euler-Lagrange equations just boil down to dl dq I is equal to the time derivative of dl dqi dot. Right, I just added on both sides. So, what the hell is this? What is in the world is this? We're going to need to do a lot of examples to solidify this in your brain right now. Let's do this. Okay. Euler-Lagrange equations. Let's go. And why do I say equations? Because right, generalized coordinates have many variables. They can be x, y, z, whatever you say. So you can have many Euler-Lagrange equations. So Euler-Lagrange equations. dl by dqi is equal to time derivative of dl by dqi dot. Okay, let me just put this on the side for reference. Now, let me do example. Example 1. Consider a free particle. Again, the trivial case. Free particle. Okay, so Lagrangian. Step 1 is the Lagrangian. What's the Lagrangian? T minus v. What's t? It's just 1/2 m, and let's consider one dimension. 1/2 m x dot squared minus, well, what's the potential energy of a free particle? Is just 0. So it's just 1/2 mx dot squared is our Lagrangian. Now let's compute the equations of motion. It's going to be, for this case, our dynamical variable is just, there's only one of them, is just x. So it's going to be dl dx equals the time derivative of dl dx dot. Okay, what's a derivative of the Lagrangian with respect to x? Well, there's no x in there. There's no x in the Lagrangian. So it's just 0. Now, what's the derivative? So first you do the inside derivative. What's the derivative of the Lagrangian with respect to x dot? Well, you carry the 2 over, you just take the derivative, it's going to be m times x dot. Just a basic derivative. Now, what's the derivative of x dot? What's the derivative of velocity? Acceleration. F equals 0, which is defined to be mx double dot is 0 for a free particle. That's the beauty of Lagrange. You can derive Newton's equations from these Euler-Lagrange equations, and they're much simpler to work with because you just need the Lagrangian. You don't need any constraint forces, you don't need any forces to begin with. You just need the kinetic energy, the potential energy, and you have Newton. I cannot say it better than that. You have Newton if you have Lagrange. Now you might be thinking to yourself, what the hell is this? This is a stupid example. Let me do something. Let me do a real example. Okay, I'll give you a real example. A pendulum. Okay, the pendulum starts over here. Now, something that I didn't mention, right? How do we pick these QIs? For example, in this system, you can pick XY. Sure, you can pick XY. But do you really want to work in XY when you have theta over here? It's much more convenient to write our equations in terms of theta, because there's just one dynamical variable, 1 degree of freedom. Here you have to turn it in y in terms of x. It doesn't make any sense. This is going to be our generalized coordinate, theta. Okay, and let's say that the length of this is L. So how would you do this Newton's way? Well, we have mg down, you have tension. Oh my god, please. Lagrange. Step 1. Oh, and by the way, the systematic way of doing this. So step 1, find the Lagrangian. Step 2, plug it into the equations of motion. And step 3, you solve. Simple, simple, simple. Very simple. Okay, Lagrangian, let's go. T minus V. And let's say this is the origin, right here. You need an inertial reference frame. An inertial reference frame is one. Actually, the beauty of this is that you don't need an inertial reference frame at all. The next example that I'm going to do is going to be different dynamical variables. Actually, technically, you do need an inertial reference frame. Sorry. Disregard that. You need an inertial reference frame. If you have an accelerating reference frame, you have fictitious forces, which is the study for much later in this course, if you would call that. You could definitely do like that too, but it's much easier if you have something that's not moving. So this is 0, 0 for our purposes. Okay, so kinetic energy is 1/2 mv squared. It's going to be, well, we're in 2 dimensions now, right? It's going to be 1/2 m x dot squared plus y dot squared. Right? Velocity is just the derivative of position squared. Waza. Now, as I said, a generalized coordinate is theta. So, what's the relationship? What's x, first of all? Okay, x is just L cosine theta. Oh, no. X is L sine theta, right? Because this is theta and this is x. So x is L sine theta. And y is going to be L cosine theta. Very simple, very, very simple. What's x dot? Is just a derivative. So L is a constant, and we have cosine theta. The derivative of sine theta is cosine theta, and don't forget the chain rule. Chain rule says that you have to tack on theta dot. Right? You take the derivative of sine theta, which is just cosine theta, but then you have to go inside and take the derivative of theta, which is theta dot. Now the same thing for y dot. Pause the video and try to do it for yourself. Okay? Hopefully you got an answer. Y dot is just L is a constant. Derivative of cosine theta is negative sine theta. And don't forget the chain rule, theta dot. So now we plug it in. What do we get? T is equal to 1/2 m. So x dot squared is just L squared, right? Cosine squared theta, theta dot squared. And then we have the negative squared is just positive, so it cancels out. So we just have L squared sine squared theta, theta dot squared. Now notice, we can factor this out. We can factor an L squared and a theta dot squared out. So we just get this. And what is this? This is just our favorite Pythagoras. It's just 1. So in total, the kinetic energy is 1/2 m L squared theta dot squared. Hallelujah. Saw how easy that was? Piece of cake. Potential energy. mgy. What's y? Plug it in. Oops, y is negative L sine theta. L cosine theta. Sorry. This all should be negative. Right? Because look, our coordinate system is 0, 0 here. So if we go down, then we're going to have negative values of y. So this would be negative L cosine theta. So this is positive. But it doesn't really matter anyway to think about it, because you're squaring it either way. So the sign doesn't matter. But y is negative because we're going down. So it's just negative mg L cosine theta. Right? You just plug it in. So this is our potential energy. Okay, we're almost done. Now we have a Lagrangian, it's T minus V. So T is this equation, m L squared, theta dot squared, and then minus negative, so it's going to be plus mgl cosine theta. Great! Step 1 complete. Now, we have theta, so we do the Euler-Lagrange equations. dl d theta is equal to the time derivative of dl d theta dot. Okay, dl d theta. Well, this term doesn't have theta. This term has theta. Yeah. So what are we going to get here? mgl is just a constant. And then we get a negative sine theta. Derivative of cosine theta is negative sine theta. And that's it. Is equal to the time derivative of the inside. What's the derivative with respect to theta dot? Well, the second term is just theta, so this term has theta dot, and this is just an easy derivative. It's going to be m L squared theta dot. One more step. What's the time derivative of this? m L squared is just a constant, and the derivative of theta dot is theta double dot. Okay, m's cancel out, 1L cancels out, and we're left with negative g sine theta is equal to L theta dot, double dot. And this equation is very easy to solve. Plug it into your computer, and you will get the answer that theta is equal to A cosine omega t plus B sine omega t, where omega is just 2, wait, what is it? Oh, no omegas, sorry. Cosine t plus B sine t. Oh, what am I? Yeah, this is what it is. Just plug this into your computer. I don't know what, I forgot what the answer is. Yeah, but you're gonna get an answer. This is the equations of motion. This is fine. If they ask you for equations of motion, you can just write this. But if you want to solve it in the computer, this is what you're gonna get. And this is the equations for simple harmonic motion, which we know by Newton that pendulums obey simple harmonic motion. So we have just derived Newton once again using Lagrangians, and it was extremely easy. Right? We just had to do the Lagrangian, kinetic energy, potential energy, and we just had to take the derivative a couple times. So now let me go into a little harder problem, but very easy still. It's all an easy process. Incline and a block. What are the equations of motion? Oh, and let's say the incline is on a surface, and it's free to move. No friction, nothing, is just free to move. right? This is m1, m2. What are the equations of motion? Now you're really going to start to see the beauty of Lagrangian's equations, right? So what's the first thing we do? Lagrangian. Even before the Lagrangian, what are our dynamical variables? Right? That's the first thing you need to know. And in this case, there are going to be two of them. One for M1 and one for M2. Okay, rule of thumb. Convenient coordinates. Well, M2 cannot go up or down. M2 can only go horizontally. So if we consider this our inertial reference frame, sorry, not there. If we consider this 0, 0, then this distance is x. So I'm not going to call it x. X is too mainstream. Let's call it d1. So the distance from our inertial reference frame is going to be d1, and that's going to be for this block, the incline, sorry. And then, because it's very convenient, right? Is in the horizontal direction, and the incline only moves in the horizontal direction. Okay, and for this block, where does it move? It only moves along the incline. So we could name this coordinate system d2. I mean this the generalized coordinate d2 along the incline because it's very convenient. Right? Those are our dynamical variables. Those are our generalized coordinates. Step 2. So step 1 complete. Right? It's very convenient. I love that fact. So now, not Euler yet, Lagrangian. Okay, kinetic energy. Well, there's going to be two kinetic energies. There's going to be T1, and there's going to be T2. So T1. Let's do T2 first. T2 first is very easy. It's just the kinetic energy of the incline. So D1 is just going to be D1 dot. Oops. Right? D1 dot squared. 1/2. Oh my god, I'm messing up. 1/2 m d1 dot squared. Right? Very simple. And now, what am I doing? Why am I calling this? This should be d2 because it's for mass 2, and this should be d1 for mass 1. So this is d2. Okay, d2 mass 2, d1 mass 1. So kinetic energy for the incline is just 1/2 m d2 dot squared. Oh my god. Okay, now the first one. First and foremost, this is in the incline, so we have to split it up into, we have to find x and y first. So I should have done this from the beginning, sorry. Let me just do this one more time. x1, let me do the second one first. x2 and y2. x2, y2. What's x2? Well, that's just d2. And y2 is just 0. It's not moving in the y direction. And now what's x1 and y1? y1 is just, well, x1, we have the incline, that's d2. And we have theta is going to be, where's theta going to be? Theta is going to be over here. If you do the geometry of the situation, theta is going to be over there. Okay, so you can see from the diagram that y1 is going to be this d1, sorry, this is d1 of the generalized coordinate from m1. So it's just going to be d1 times cosine theta? Negative, right? Because it's going down. It's going down. So negative d1 cosine theta, right? Because theta's here, d1's there, and yada yada. And this one is just going to be d1 sine theta. Positive, because it's going this way. Okay, very simple. Very, very simple. x1 is d1 sine theta, this direction. y1 is negative d1 cosine theta. Okay? Very simple. x1, x2, y1, y2. Now, kinetic energy. T1. It's 1/2 m x1 squared m1 x1 dot squared plus y1 dot squared. Right? just 1/2 mv squared, so 1/2 m1. Well, what's x1 dot? X1 dot is just a derivative of this. The derivative of this, well, sine theta is just a constant, right? This theta is fixed, and it's just d1 dot. And y1, same thing, negative cosine theta, d1 dot. Oh, we forgot a big point in this. We forgot a crucial one. This d1 is displaced. Remember, we have our inertial reference frame is displaced by d2, right? This x is going to be d2, sorry, plus whatever d1 sine theta is, right? Over here is going to be d2 plus this little bit extra. So you add d2 in there. That's very important, because if not for that, we would just have d1 sine theta, which would just be a very, very small distance, right? But our inertial reference frame, we have this d2, and then plus this d1 sine theta from the diagram. Okay, so when we take the derivative of that, we're going to have, of course, d1 dot sine theta, and then plus d2 dot. Right, just take the derivative. Okay, and for x2, you do the same thing. x2 dot is just d2 dot, and y2 dot is 0, because y is 0. Okay, so it's just 1/2 m. Let me do it over here. 1/2 m1. What's x1? x1 is this, so it's just sine theta, d1 dot plus d2 dot, square all that, plus y1, which is negative cosine theta, d1 dot squared. And now we just have a bunch of algebra. So let me just do this real quickly. 1/2 m1 sine squared theta, d1 squared, plus d2 squared, plus 2 d1 d2 sine theta, and then plus cosine squared theta, d1 dot squared. Right, and just expand everything. This is the only hard part was to find x in terms of our generalized coordinates. That was the only hard part. And now we just plug it into the kinetic energy, and we simplify a bit. What can we do? We have sine squared and cosine squared, so this just becomes d1 squared plus d2 squared plus, and then we have this term, 2 d1 d2 sine theta. Very easy. That's the kinetic energy of the first one. The kinetic energy of the second one is just 1/2 m2 x dot squared plus y2 dot squared. y2 is 0. x2 is just, by this equation, 1/2 m2 d2 squared. Very, very easy. And thus, the total kinetic energy is T1 plus T2 is going to be 1/2 m1 d1 squared. I'm going to expand everything, plus 1/2 m1 d2 squared, plus 2 cancels out, m1 d1 dot d2 dot sine of theta, plus 1/2 m2. We forgot about this term, d2 dot squared. Okay, what's the potential energy? Well, it's going to be v1 plus v2. Potential energy of the incline is 0. It doesn't move. Potential energy of the first one is just mgy. And I forgot. What is y? Y is negative d1 cosine theta. So negative mg d1 cosine theta. Now we have our Lagrangian is t minus v. This is going to be this long expression, 1/2 m1 d1 squared plus 1/2 m1 d2 squared plus m1 d1 d2 sine of theta plus 1/2 m2 d2 squared, and then plus mg d1 cosine theta. Okay, tell me how easy that was. You find xy. Let me just reiterate the process. It's very easy compared to all the math you're gonna do for solving, splitting up the components and everything. This is much easier, right? You have the generalized coordinates, very convenient, Very convenient coordinates. And then you find x1, x2, y1, y2 in terms of the generalized coordinates, d1 and d2. You take the derivatives, even easier. You just put a dot on top of them. That's literally it. And then you plug it into the kinetic and potential energy. It's just a lot of algebra, but much less than you would do solving any hard, extremely hard. To do that problem with Newtonian mechanics would be almost impossible. Let me just put it like that. So we have this Lagrangian, and then we just plug in two our Euler-Lagrange equations, and we're going to have two of them, right? Because since we have two generalized coordinates, we're going to have two generalized equations. We're going to have for d1 and for d2. So let me do it for d1 first. So the derivative with respect to d1 is equal to the time derivative of dl with respect to d1 dot. Okay, what's the derivative with respect to d1? This is d1 dot, d2 dot, okay, d1 is right here. It's just going to be mg cosine theta. Right? What's the derivative of this? It's just mg cosine theta equals the time derivative of the derivative with respect to d1 dot. Well, we have this term is just going to be m1 d1 dot, and this term is d2. Oh wait, we have this term is going to be, we're taking the derivative with respect to this term, so everything else goes. So it's going to be m1 sine theta d2 dot, m1 d2 dot sine theta. Okay, one more step. Very easy. Mg cosine theta. Oh wait, which m is this? M1, right? Yeah. Because it's the incline that has potential energy. M1g cosine theta is, and we just take the time derivative. So d double dot and d double dot. And there you have it. Oh, m's cancel out. Even better. So we're just left with g cosine theta is equal to d1 double dot plus sine theta d2 double dot. And that's our equation of motion. But we have another one, right? This is only with respect to d1. Now with respect to d2. So dl d2 is equal to the time derivative of dl with respect to d2 dot. Okay. One more time. Now with respect to d2. So dl d2. There are no d2's in here, so that's just 0. So 0 is the time derivative of what? dl with respect to d2 dot. We have a d2 dot here, so that's just m1 d2, just a derivative. And then we have this term. But we're taking the derivative with respect to this now, right? d2 dot. So it's going to be m1. So we take everything else. m1 d1 dot sine theta. And then we have this d2 over here, which is going to be, you bring the 2 down, m2 d2 dot. Okay, and then one last step. We just take the derivative, so 0 equals m1 and then d double dot plus m2, this one, d2 double dot. Oh, I could put these together, right? Because they're both double dot. So I'm going to put that as m1 plus m2, d2 double dot. And then the last one, m1 sine theta, d1 double dot. Okay, that's our equation of motion. So we have one equation of motion and another equation of motion. And look at this. We have d1, d2 double dot, d1 double dot, two equations, two unknowns, and we can solve. You saw how easy that was? We literally, the only hard part of this whole thing was finding our generalized coordinates and representing them in terms of x and y. And then that's it. You find the kinetic energy, find the potential energy, you find the Lagrangian, and then you just take the derivative. And this can be applied to every single problem, even much harder problems than this. It's just the same procedure. Okay, so I hope this sheds some light. Thank you.